with the interacting electron gas, where I just wrote down the partition function here once more. And then we implemented what is called the Hubbard-Slattonovich transformation, which is kind of an inverse of a Gaussian integral. So one introduces a new degree of freedom, which is a bosonic field, to decouple the interaction terms. So what one arrives at is a theory that is quadratic in this Hubbard-Slattonovich field, which was used to decouple the interaction, and now quadratic in the fermions. Okay, so this is just mathematical identity. And so I tried to explain. So this was for the case of the interacting electron gas. There is a lot of freedom how to do this decoupling. So there's, on one hand, there is like technical degree of freedom how you want to like divide the phi coupling here to the electrons in the quadratic. Of course, you can multiply here with some factor, which you should then also divide here or multiply here. So there's a lot of freedom. So this was chosen such that the coupling between the electrons in this Hubbard-Slattonovich field is more easy. But then more importantly, we said there's different channels one can actually decouple the interaction. I just do one more try because I think the last time I really failed to explain this. I just one more try to explain this the difference. So there's actually, we said there's three, like if you start out from a general interaction term, there's three different channels you can decouple in. Which we call the direct exchange and the Cooper channel. So here we decouple in the direct channel. So this is like the first two steps in the general program that we formulated, and we will then continue with, following the entire program that we formulated in the beginning, 5 steps to derive an effective theory for the interacting electron gas, where one now gets somehow rid of the microscopic, which you see the microscopic degrees of freedom has a formulation time in the bosonic field phi, which is Hubbard-Slattonovich field. And we also said, well, here the phi really has, immediate physical interpretation. So we see that the phi here is just like coupling minimally to the electrons in form of the electric content of the electromagnetic potential. No? So this is just electrons in the fluctuating electromagnetic potential, so only the electric, the scalar part, and the fluctuations of this part is just given by the bigger photon propagator 1 over q squared. Propagator 1 over q squared. So we said then, made a detour to the general Hubbard-Slattonovich transformation and the different channels. And I tried to explain the 3 channels that appear, going back again to the interacting electrons, where one then has the 3 channels. So let me recall you, we somehow put these 2 variables into one degree of freedom, which is phi, and these 2. There would have been other ways to put these 2 in an effective degrees of freedom, would have been exchange all these to the paired channel. And in the interacting electron gas, what is always like the guiding principle is that there one has a large number, which is the density of the electron. So we are considering the large density limit, which means the Fermi surface is large. And what I try to explain is that if you start out from this general structure, so you have electron-electron interactions, you have 4 participating fields, so 2 electrons, 2 holes, and due to momentum conservation, then one has 3 free momentum. So I try to motivate that if you have in such a scenario 3 free momenta, but you want to have all close to the Fermi surface, there will be 2 free momenta close to the Fermi surface and 1 small momentum q. And what you want to do somehow is that this effective field of freedom just depends on the small q, which means this will be in the degree of freedom which is only slowly fluctuating. Okay, you somehow get rid of the high energy, the high momentum scale, which is the Fermi momentum, and try to derive an effective theory which now only knows something about the small momentum q, which is slowly varying. So this then allows to derive, you see that like you can do gradient expansion because this is slowly fluctuating an effective theory in terms of this new degree of freedom. So let me just once more try to point out the thing that if you have 3 momenta and once you have all close to the Fermi surface, you will see that there's only the 3 combinations of momenta that you, or channels that you end up with, which is the direct exchange. So let's consider here momentum space px, py, so 2-dimensional system. This is a constant p squared. So let's say we have quadratic dispersion, so this would be the energy. And this here is, let's say, the Fermi momentum. We want to consider an effective theory living in some energy shell around the Fermi surface. Okay, so this would be the broadening typically of Aula energy. So let's just consider, like, if you start off with any momentum in this momentum shell, so this would be some state P, and this is scattered in, let's say, into another state P plus Q. Okay, so if you just now take a generic other momentum, let's say P prime, and then due to momentum conservation, this would be scattered into state here. Okay, so this should be, let's try to, like, this should be the same momentum, or this would be P prime minus Q. Okay, so you see, well, this doesn't end up at the Fermi surface, so such processes just don't work. You cannot just take a generic P, let it scatter into some P plus Q, take another generic P prime, and then take P prime minus Q, because you end up not with all states at the Fermi surface. Okay, so that's the first observation. So there's some fine-tuning which you need to do to arrive at the scenario that all states are close to the Fermi surface. So one obvious somehow thing is, well, if this here just scatters by a small momentum, okay, so this scatters from some P into some P plus Q, then, well, you can take any generic other one, and let's say here P prime, and if this scatters by the same small momentum, well, it will be still in the same, on the same Fermi surface, okay? So if you take a small momentum Q scattering here, this is possible to take P and P prime arbitrarily, okay? Let's just make a picture what this would correspond to. So this would be taking some, let's say, P plus Q, scattering into some small p close by, and then you take an arbitrary p prime, which is scattering into p prime plus q. Okay? So this would be like pairing the interaction in this way. This would be the direct channel. Okay? Just a small moment. Now there's a second choice which one can do, and this is if we take this momentum p and let it scatter into some generic other vector, which doesn't have to be close by but can be anywhere. So this is like p, and this is, let's say, p prime, or let's say start off p prime and p. Then the other option is, well, if you now take just close by states to each of them, like to this one, and this will then scatter by momentum close to this one here. Okay? So that's the second option. If you scatter not into closed state, but scatter into an arbitrary other state, but then consider close by states, well, then again, you can achieve that here now p prime and p are anywhere, and these are just shifted by a small momentum q. Okay? So this would correspond to the direct channel. So you start out here from some you start from, let's say, p prime, you said, and scatter into p, and then you just take momenta in the vicinity which scatter in the opposite direction. Okay? So this would be pairing these two. So what are now close by are not anymore that you scatter the same here, but you scatter the one, they scatter somewhere, and from a vicinity they scatter a different electron here. So you saw in the first channel, if you put in spin, you said this electron scatters somewhere here, so this would correspond to the same spin component. Okay? So here it's actually just different electrons, so here now these can have different spins. So this would be the exchange channel. Okay? So that's the second option. Then, if you think about it, quite a lot, you can then come up with a third combination, which is, well, take again this one p, which is scattered into an arbitrary p prime, or the p prime is scattered into some arbitrary p. Now, if you take the momentum here minus in the vicinity of minus p prime and minus p. So this now sketches into some arbitrary, but here we just scatter by the reflected momentum. Okay? So that would be the third channel, where I now, for simplicity, I mean to draw it easier, I just let's say flip here, the orientation up here. So you have a P being scattered, or some P prime scattered into some P. And then you have here some closed P prime plus Q being scattered into some P plus Q. Okay? So now you have these momenta are close by in momentum space. Okay? So this would be the Cooper channel. Okay, so this is like, trying to get too expensive, but there's like 3 options, and it's good like if you look at this one. So if you have the constraint, 3 momentum, all 3 close momentum, there's 1 small momentum involved, and this small momentum can be split in different parts, which make up the 3 channels. Okay? Okay, so what we did here in the weakly interacting electron gas, and this was based on our intuition from the diagrammatics, we decoupled here the field actually in the direct channel. So you see here the density couples to this field phi. So there's no spin flips involved. It's an electron in the hole, like density with the same spin, so this is a direct channel. Okay? So then let's get back to the interacting electron gas and see like how we can perform the rest of the program now for this action. So let me just write down some more comments here. From the diagrammatic analysis, we found that the RPA approximation is a good approximation in the large density limit, where like the building blocks for the diagrams that we drew could be all made up out of these type of diagrams. Okay, so where here's like a spin sigma flowing, here's spin sigma prime. So from these kind of diagrams we made up the bubble diagrams, no? From this kind of building blocks we made up the bubble diagrams by connecting this to this kind of ring diagrams. Okay, so we saw that the elementary building block should be that we pair these into the effective degree of freedom, and this is exactly what we did here. Okay, so the phi here was in the density channel. So which would be this channel here. Okay. So this is what happened up to here. Now we are left with 2 Gaussian series, one for the electrons and one for the, let's say, photon field, which are coupled. But the idea is exactly that you want to have an effective theory where we don't care anymore about this high energy scale, the Fermi momentum. Fermi momentum is a very large energy scale. Okay, so always should have this in mind. This is a large Fermi sea. This is like the energy of the Fermi energy. And all we want to have is an effective theory which only knows about this scale that's set by temperature or by velocity times Q, where Q is the typical fluctuations of the soft field, and we don't want to talk about this large energy anymore. Okay? So we want to integrate out everything that has to do with large energies to arrive at a low energy theory that just knows about this energy scale. Okay? So this we can now easily do, because this theory here is quadratic in the fermions. The fermions have the propagator which knows about the large energy scale. This is a softly fluctuating field. So let's integrate out the high or the large energy degree of freedom, which is the fermions. Okay, so that's the idea, and try to derive an effective theory for the phis. Okay, so after HS is for Hubbard's Markovitch, no? So after Hubbard-Satornovich transformation, we are left with quadratic integral in the electrons. And we know how to do quadratic integrals, so which can be done exactly. Okay, so we can do what is in this program was training microscopic degree of freedom for the effective one, which you can here summarize by integrating out the fermions. So what do we get? We have the partition function written as a double integral over phi over the electron fields. So we can do the Gaussian integral in the electron fields. This will just give the determinant, no? So we have the determinant, and then we have the partition function as an integral over the effective field phi, which has now this quadratic action, and then we have the determinant which contains the propagator of the electrons in this fluctuating field phi. Okay, so if we integrate out the electrons, which would be step 3 in the general program that we formulated, then we arrive at partition function. Now I change here to momentum representation or momentum representation, because there the propagator for the moments is diagonal. So that's just copying the first part of momentum space, and then we have the determinant, which I write the way I omega plus t squared over 2m minus 2 plus. So there's some L to the cube if you go to the momentum representation, to the momentum transform. And this here inside is an operator that will write the inverse of Green's function or propagator, and this is the G is the Green's function. That's just the electron Green's function, GF like Green's function in presence of this fluctuating field of fluctating field phi, or if you look at it, it just couples as the electro potential also. Just write out the t to the minus 1 is minus I omega plus t squared. Okay, so this is just, I mean, a mathematical identity that we're using here, but then one has to be a bit careful with this operator here, okay? So this is often, I mean, one has to get used to what is written here, okay? So in a way you can think of this as being a large matrix which has structure in Matsubara frequency and the momentum space, okay? So let's just consider this part here, and all the problem or confusion sometimes is if you look at this operator, that's actually the one governing the quadratic action of the electron. So you see that this has a time derivative, has spatial derivatives, and has a potential. So this can be viewed as an operator which can be written down in different bases. No, it can be written down in the momentum or in the space basis. So now the problems here are what makes it a little bit not immediately clear how to understand everything is that if you look at this, well, this here is, for example, diagonal in Matsubara space. Okay, this is diagonal momentum space. However, this phi here is in real space. This just multiplies as a local term. Okay, so this is like local in general form momentum space, and this is local or diagonal in real space. Okay, so there's always then some let's say technical one has get used to it. You cannot immediately write down this operator easily because I mean, or you write it down in momentum space, but then you have to be careful how this acts in momentum space. Or you write it down in real space, but then I mean, you want to have like the inverse of this. You know, this is also not such a simple matrix. You like the matrix which has in the off-diagonal entries. Okay, so let's just first write down this observation, and this is again like the thing one has to get used to. Then in all the expression or the calculations that one is doing in the following, one always has to keep this in mind. Okay, so we have here like a determinant of a large matrix, but this matrix, well, would be simple if it was just this, because then it would be just, you can write it down in the most convenient basis, it would be just in form momentum, or it would be simple just like this. Okay, but if you look at it completely, it's a little bit more complicated object because there's two parts which are would like to be diagonalized in conjugate like basis. Okay, so the Matsubara and Hilbert space components are as follows. Just write this down. So the omega is just a diagonal operator in Matsubara space. P squared operator is a diagonal operator in momentum space. And the phi operator is a diagonal operator in the x house, so this is like 3 coordinate and imaginary kind of x house space. Okay. So what will then appear, so we will see, there will appear like traces of products of these operators, okay? So just to make sure, like the determinant here is the product of the eigenvalues. So if you want to diagonalize this, for example, but here it's hard, but it's a product of all the eigenvalues. A trace in the same way would be just a sum of all internal degrees of freedom, no? I mean, like the trace of the internal degrees of freedom. So the trace would contain, you can write it down if you like, as a sum over momenta and Matsubara frequencies, or you can just write as an integral over d-dimension space and imaginary time. Okay, and just to make sure what is meant, for example, if you see product of this type where you have the Green function, which can be now the general Green function, then you have the potential phi and the g. This here now corresponds to a matrix product or an operator product, so you can choose a basis that you like. And let's say you want to consider in real space the RR prime component of this operator. Okay, so how would you write this? Well, you would perform here just the usual matrix multiplication. Okay, so you have some internal index where you sum over. So the R is fixed. Then the R1 here comes from the trace, GRR1. Now you have phi, but this is diagonal in real space, so this is just phi of R1 because this is just diagonal, and then we would have here GR1 going to R prime. Okay, so this would be an example where you look at this matrix here, which is obtained from matrix multiplication, operator multiplication in the R basis, and this is RR prime. Okay. So now if you consider the same, let's say, momentum space, so let me just keep it general. So oftenly you will have here a G, take as a reference point one, let's say where you don't have the phi, then this would be diagonal momentum space, but let me just write it down once general, where the G doesn't have to be diagonal momentum space. So then this would be given by now two momentum summations, and I will explain why. So this would be P1. Now comes like the essential part. So here we have, if we take the product, just one internal integral over R space, and this is because phi is a diagonal operator in the R basis. Okay, so this is why we have here only one. But now if you want to write down the same thing, let's say in the P basis, now the phi is not diagonal in the P basis. Okay, so what you actually have to do, you have to look at the Fourier transform of this in the P basis, and then you will see that the phi is not diagonal in the P basis. So in general, this would be then G pi 1, pi 2, and then you go to G pi. Okay, so this would be in the P basis. Noting here that this is not diagonal, but then you can now look at this matrix element phi of P1 minus P2, and this is just, you see from Fourier transform of this, that the phi of pi P1, P2 is just, so the matrix element 1, 2 just depends on the difference of the momenta. Okay? So this phi of pi 1, P1, P2 is just phi of P1 minus P2. This is just from, Fourier transform. No, Fourier of a Fourier transform of a product gives you like a convolution. No? So this is just. Okay, so one has to be careful that, well, depending on the basis you work in the X basis would be diagonal, but in the P basis this is not diagonal, and you know that the matrix elements P1 to P2 are just the differences here. Okay? So this is one way to keep this like organized in your head. This is big matrices, P space, this is diagonal, this is off diagonal, this is. If you don't like this too much, well then go to the R representation as here and do the Fourier transform, then you're safe that you're not doing any mistakes. Okay? So this might take some time to get used to, but okay, so one is here, so again, one has to do something to get used to. Then comes like the usual trick, so we have here now a determinant of an operator. And what we want to do is we want to write this as an effective action for phi. So we can write the determinant, we can always write the log of the determinant as E of the trace, or no, you can write the log of the determinant as a trace of the log of the operator. No? So there's this operator identity, which is the log of the determinant of an operator is the same as the trace of the log of the operator. So this is a much used operator identity. Which actually, if you want, like mostly we're actually always dealing with some diagonalizable matrix, so you can just make this like prove this for this kind of matrix by going to diagonal basis. Okay, so looking at the eigenvalues. Okay, so this is an important operator identity, which probably you also already know, and which now helps us here to write this as an E of the trace log. Okay, so we have another exponential, so we can write this actually in a more nicer form, how we would like to have it, the partition function as an integral d phi, where we have each phi is weighted by an exponential of the action, which now consists of this term, and then we have the trace log of this operator here. Okay? So if we use this identity, we can write this in a nice form. So we have now arrived at the representation of the partition function entirely as a function integral over this effective field, which is now weighted by an action, which is here. So just copy the first term. And then we have minus the trace log of this operator geophi. Okay? So this is just using this identity, and now we have like arrived at an expression of the partition function type of this degree of freedom phi, where here the trace has to be understood as the sum over all internal degrees of freedom. Okay? So as said, or you write as integrals over R, or you write as integrals over P, but please take into account that G versus phi and so on is always understood as matrix products in the space you chose. Yeah? Aqui você pode usar aqui o log. So, log de A menos 1 é menos log de A. Sim, também funciona. Todas essas propriedades, na verdade, você sempre pode pensar simplesmente nos eigenvalores, porque esses são diagonalizáveis, nos nossos casos, você pode pensar na diagonal base, tá? Então tem que ver com esse signo aqui, mas se pode escrever isso assim, ou com esse menos. Tá. Agora nem sei, vamos qual seria o certo? Então assim está certo. Não, assim está certo. Bom, isso vai seria o menos por causa do menos aí. Então vamos, eu acho que está até mais confortável de trabalhar com esse, mas poderia bater, mas assim está certo. So there's one more thing that we have to take into account here, which was always important, that here we are dealing with a system where we had the charge neutrality. Okay, so we always excluded the Q vector being the zero component, which was not there because of charge neutrality. Okay, so this summations over Q here always means, well, we excluded the Q equals 0. Well, here it's 0 anyway. But also in this field phi here, the Q equals 0 component is excluded. Okay, just so we only consider these four momenta due to charge neutrality. Okay. So let's see what we did so far. So far, I mean, still everything that we did was exact. No, so the Hubbard-Satonovich transformation we said isn't just an exact identity. Integrating out the fermions and rewriting this and using this operator identity, it's all exact. Okay, so this contains entire microscopic information that we had. So everything up to here purely formal and exact. Purely formal manipulations, which were exact. So what we in fact managed was, so we completed the steps 1 to 3 in the general program. So managed to trade formulation in microscopic degrees of freedom, which depend on the high energy scale, with the electrons, for one in the auxiliary field of higher complexity, phi. Okay? So this is all exactly, and as like emphasized several times like last time, I mean, the entire game is, well, we could have done this in every channel that we wanted, but the essential part then is that now we are going to like the two remaining steps, which will be approximations, which will, starting out from this object, which is still very complicated, try to derive an effective theory. And this effective theory only really, I mean, works well if this phi, if like the entire information here is in, if we would take into account like all this operator here, which looks innocent but is really highly complicated. So the entire game is, if this phi is really like the effective degree of freedom that we're interested in, then the slowly fluctuating part, low energy excitations of this field should incorporate all the physics. So this means that if we make now a low energy expansion in this field phi here, we can get rid of this trace log, which is highly complicated, and derive some effective theory. And the entire, I mean, problem is to have done this in the right way, that this low degree of freedom phi really captures the physics that we're interested in. And that crucially depends on like which channel we decouple in. And this is like based on typically on the diagrammatic intuition that we first have. Okay, so this is now the remaining step, so this is all just mathematics. So now comes like the physicist approach, where you say, well, there is some large parameter here like density, and this allows us to do some expansion, and if we did it all with the right physical intuition, then this expansion leads to an effective theory which captures all the physics that we are interested in. Okay. So in these two steps are so what do we do? We do first a saddle point analysis of this. So we look at mean field solutions of the saddle point equation, and then do an expansion around the mean field solution. Okay, this is in the effective theory. Now I already said that this is like the simplest example where we can do such a program, and actually it's not so interesting, because what we will find that the saddle point equation just will single out the trivial solutions, which means phi equals 0 will be a solution of the saddle point equation. And this just reflects that, well, if phi equals 0 was the right mean field solution, this means that the non-interacting reference point was the right reference point to formulate the perturbation theory around. Okay? This is actually what we did in diagrammatics, so we shouldn't be too worried about this. This will be just confirming that our diagrammatic analysis, where we didn't think so much like what is the right reference point to make perturbation theory around, we didn't think so much about, but this will then just define this approach. So this will be this, but then we will still study at least one other example where we see that this mean field equation can be interesting, because it can give also solutions which are not trivial. And this then really means that there is some phase transition going on, and the non-interacting reference point is not so interesting. But this will be only the second example that we're going to discuss. So here, so we'll do all this work, but this is in a way not leading to so much interesting things. It's just confirming that what we did before was the right thing to do. Okay? So let's come to the saddle point analysis, which is step 4. General program, and which is taking function derivative of the action say momentary representation set this to 0, and this should hold for all Q which are the one which we consider, so the one where we exclude the 0 mode of charge neutrality. Okay, so we have to do this kind of derivatives. Now, let me just mention one more thing. So what will always appear is we will have this kind of functionals, okay? And this here, as said, is not so easy. One has to get used to this thing here. So because this is not just a function, but this is a large operator or a large matrix, which you can think in some of the space. So what you typically have to do is you have to know how to do like analytical manipulations with this object. And the nice thing here is that there's a trace in front of this, and this trace like hugely simplifies all the calculations. So let me just give one example. Like if you consider the derivative, just the normal derivative of such an operator, you can show that due to the trace, it just amounts to a very simple operation. So I don't know if you're familiar with this kind of things, but maybe I just repeat this here once, because this is the kind of manipulations that you have to do. So you have to know say how to do derivative. So this is just like a comment here, small comment. Let's say where you have something like trace, and then you have the function of some operator. Okay, so this would be the type of problem that, for example, one encounters here. One wants to do derivatives, so one can generalize this also to the function derivative, but we have a trace of a function of an operator. Okay, so this is the function would be the log, and then so how do you do this? And the statement is that this trace here is actually working a lot at our favor. So let's see how this works. So let's consider an operator which here is diagonal in x, so all of x. And let's say x can be coordinate or just some parameter. So you can then also generalize this that this is an operator of some field, and the derivative then would be the functional derivative. Parameter and let f be an arbitrary function. Okay, not so arbitrary, because typically what we're considering is functions like log or exponential or whatever, cosine, sine. So it's functions that have like power series representations. Okay, so let's consider arbitrary function with the power series expansion. So f of z, where z is now a normal number, not an operator, so it can be written as this ends here in brackets, the n's derivative, and faculty. Okay, so this is just a normal Taylor expansion. So then you can write the derivative of the trace of f of O, just in terms of this power series. So we have a trace, and we have here the coefficients from the Taylor expansion, and here we have the product of the nth product of the operator. Okay. So now you have here the derivative is a linear operator, so you can just put it in here. Okay. So it will act on this product, so it will act like on the first component, leave the other invariant, the second, and so on. Okay, so we can here just apply the chain rule. So I put this in here, and then there will be like del x of On, which is del x O O to the n minus 1 plus O del x O, O to the n minus 2, and so on. Okay, so there will be this entire stream. Okay, and then comes like the observation that, well, normally you have a problem here because the derivative of O and O do not have to commute. Okay, so del x of O times O to the power of n minus 1 plus O del x O times O to the n minus 2 are generally different operators. Okay, so you have here like a long series of terms, and there's no reason why they are the same. Okay, but then you see now what I said, that this trace here is like our friend, because trace means that we can cyclically permutate like the expressions inside the trace, which means, okay, these are different terms, but there's no reason, or you can just use cyclic invariance to put this on the same side. Okay, and this we can do in every term. So we can, due to the trace here, organize all the expressions as just, let's say, keeping the derivative at the first term, and then O n to the minus 1. So we have n terms which are all the same. Okay, so we can, due to the trace, let's say cyclic invariance of trace, we can write this as the sum over f to the power n at 0. Then we have n faculty, then we have n times the same term, and we have here trace over del x O to the n minus 1. Okay. But then we see, I mean, just the usual thing. So the n and the n faculty give us an n minus 1 faculty. Then we have here the derivatives, which can then be, so the zeroth term doesn't contribute, so constant. So this is a sum which now starts with 1. So we can organize all this with this O to the n minus 1 as a derivative of O, no? So this would be f prime of O. So we can just write this here as a trace of in this case, I write now the derivative to the right because it's clear that it just acts on the right. So we can write this here as f prime of O, which would be all these terms with O to the minus 1 times the derivative. Okay? So we see that because of this trace here, we do not have to carry too much about the derivatives, because normally all operations that one do just can be generalized from the normal functions of numbers to the function of operators. Okay, so the problem when changing from functions of numbers to functions of operators is exactly due to this, that all derivatives of operators and operators themselves do not have to commute, but the trace then makes everything nice, and we can just work as usual. Okay, so let's see if one can see this. So what we found here, thanks to trace, the differentiation diff can be carried out as if f of O was a usual function. Okay, so that's what we found here. How to do the derivative? Well, thanks to the trace, differentiation can be carried out as if the function of the operator was just a usual function in a variable, in a commuting variable. Okay, so this is was just a small comment, so we can come back to the derivative. So now what we want to do is a functional derivative of this term. So let's do it step by step. Function derivative of this expression and of this expression. So first, quadratic part. I just gave this now different names, so q prime, to make clear like these different variables. So if we differentiate with respect to phi q, we can get two values. Once q equals to q prime, and once q equals to minus q prime. Okay? But then due to the squared here, they will just give the same contribution. So this will be giving just 2 times q prime y of minus q. Okay? And the 2 is due to the fact that this can act on this and on this big value. Okay. So that was the first part. And the second part, let's write it. Here, of trace log to the minus 1 phi. Okay, so the first thing is, well, what we learned first is that this here, this derivative due to the trace can be done as that of the null function. So this will give the log, will give the inverse of this, and then we take the function derivative of this term. So this will give trace of g, and then we take the function derivative using the inside of g to the minus 1. Okay, so this was due to the thing that we just noticed. So this trace now here is like, depends on what you want to do, real space, momentum space. So let's take momentum space. And there should have been one thing that I should have noted here, that this trace also, because the electron still has the degree of freedom of spin. Okay? So the trace not only is over the internal space like momentum Matsubara, but also had a trace over spin up and spin down component. Okay? So if you look at this trace here explicitly, you can write this as 2, which is due to the spin, summation of a spin up and down, because the Green's function doesn't really depend on the spin orientation. And then we can just write it, let's say, in 4 momentum space by using that the G will be in general a matrix in the momentum space. And then we have G minus 1. And here we take the Q2, Q1 component. Okay, so this is just writing the trace here and understanding that this is a matrix multiplication. Now notice again, like we just say once more, if the phi wasn't in here in this Green's function, then the Green's function would be just, okay, it's not written down anymore, but just of the diagonal part, okay? So then it would be easy, but because the phi is in here, the phi is diagonal in X, so it's off diagonal in Q, so this has really a matrix structure, okay? So that's why this is like. But now we have here the derivative with respect to phi of Q, G to the minus 1. And G to the minus 1 just had like, consisted of G to the minus 1 was minus I omega, no I don't know, like this is sine minus di phi. Okay, there might be some signs which are probably here minus and plus, minus plus. I don't recall the signs, but the statement here is, well, it had like different parts, and G to the minus 1 depended linearly on phi. So the derivative here will only act on this matrix here. Okay? And now what we do is the derivative with respect to phi of Q. So we have to recall how this matrix, the Q2, Q1 component of this matrix is. Okay? So let's recall that phi is an off-diagonal matrix. So it has entries in Q space everywhere here. But at the Q2, Q1 component, we said, like, if you look at it from the real space representation, this momentum structure comes from having a product in real space. A product in real space translated in convolution. Okay, so this means that this component just depended on Q2 minus Q1. Okay, so these entries here depend, let's say, on Q2 minus Q1. Okay, so we have to take the derivative here actually of phi Q2 minus Q1. So what this fixes is that Q2 minus Q1 should be Q. Okay? Is this clear, or, I mean, one has to get used to it, but, okay? So if we use this, then we get Q1, Q2, then we have G, Q1, Q2, and here we have Q1 minus Q2 should be equal to Q. Okay, so this is just from the derivative with respect to this. Okay, so we can then of course just do the sum over, let's say, Q2. Then we have the sum over Q1, and Q2 has to be Q1 minus Q. So Q1 and Q1 minus Q. Okay, so this is what this derivative gives, and then I just forgot, well, there was some factor E times I over L to the cube here. This was due to the Green's function to the minus 1 had still the prefactor I times E over L cubed. Okay? So that's the second derivative, and notice here again that this Q that we are considering has the component not equals to 0. Okay, this is charge neutrality. So this Green's function here that we are considering is really only, like this term is only non-vanishing if we look at an off-diagonal term. Okay? Questions, or maybe just one more comment, like if one gets a little bit lost about this game of having phi diagonal in real space and the propagator diagonal in p-space, it's always good just to think of diagrams. So what is happening there is, like, for example, the product G, you can just think of, you have a Green's function G, you multiply with some phi locally, and you have a G going out, okay? Like if you do the Fourier transform, then you know you have like a GP coming in. This photon field can transfer some momentum Q inside here, so this will then be G plus Q, okay? Or if you like, you can write this as P prime, and then this here would be just P prime minus P, or Q, depending on if it goes in and out. Okay, this is exactly like the structure that we, for example, well, yeah, use in the multiplication. So it's always like, if you think about it, don't like get lost, think in terms of diagrams. G is diagonal in P typically, it's like the free Green's function to gets a reference state. This is a local field, so this like inserts somewhere momentum or energy, and due to momentum conservation, this then absorbs this into this matrix product structure can be always used with it. Okay. Não, dividem seus mesmos. Dividem seus mesmos. Okay, so now with these two things, well, we see that the mean field equation is given as follows. So it's beta 4 pi L cube Q squared 5 minus Q Q1 G Q1 minus Q, and this is 0. Okay, so this is the mean field equation that we are looking at here. And then so when you're looking at these kind of equations, well, they can be quite complicated in the beginning, and you can look at different kind of solutions. It can happen that you have different kind of solutions. So first, I mean, you can try to look at the most simplest case. Okay, so the most simple case in our context is, well, we start out from a homogeneous problem. So there wasn't any reason why, I mean, we had electrons freely moving against the homogeneous weird out background. So the interaction is translation invariant. So there's no reason why we should first look at solutions which would break translation invariance. So the simplest solution to this problem one can look at would be just the homogeneous solution, okay? And then you see, well, if it's homogeneous, then this here just vanishes, and here, well, we said that this only, like this, if you look at the derivative, only gave a finite contribution if one had here Q1 minus Q, so where this was different from this. So in the homogeneous case, this would be just the same, it would be therefore vanishing, so that it doesn't exist. Okay, so one sees that here, well, as said, there can be problems where it's more complicated. Here actually one can immediately identify that the simplest ansatz that one can make, and which is always guided by physics, already gives to a simple solution, namely just homogeneous solution, which then due to charge neutrality has to be zero. No? So phi of q being constant, and this is in zero. So this is a solution here. Now, I write this down, but just want to make a comment. So the idea is always one encounters here a mean field equation, which can be in general quite complicated, but a good idea is always to first look at the simplest solutions and see like what the consequences are. It turns out that in this problem there can also appear solutions which are not constant, like charge density wave solutions. And maybe we'll have time to look at one of these examples, but we look at least at an example of magnetism where you don't have a simple solution. So there can be more complicated solutions for a problem, and actually there can be solutions which break the symmetries you started off from. So what we said is, well, we start from a translation invariant system, so let's just look for homogeneous solutions, because I mean, we start off from a translation invariant system. That can be fine, but doesn't always have to hold. So there can be like symmetries in the problem that you have, but the solution of the equation can break the given symmetry. Okay? And this then leads to interesting physics, and this, okay, we'll see like in a simple ferromagnet, you can already see this, or like in superconductors, and always leads to this kind of Goldstone low line mode. So this can be interesting. Just because some of you do the disordered problem, so there's also like, just very briefly mentioned, so this one you can do the replica trick, for example, and where you have everything completely democratic in the replica, but there's some really complicated, like it took a long time for people to understand, but there can be replica gradient solution which also contain a lot of interesting physics. So that part can be really, I mean, can contain a lot of physics, which sometimes can take a while to identify all the interesting things going on here. But in our case here, we don't deal with everything so far. So we are just considering here a simple problem. So we say that we have a homogeneous problem. So the first guess, which doesn't always have to be the best, but well, first one should start with looking at the simplest case and then see what the results are. So here the simplest guess would be that this is just some constant value, because you start out from a homogeneous case and one sees actually that the action of spatial or temporal fluctuation is suppressed. The action suppresses this. But then here in our case, due to charge neutrality, which fosters that the Q vector 0 component, the homogeneous component is 0. So we have this condition, and this then means that we have a trivial mean field solution. or trivial mean field, which is the solution of the mean field equation, phi bar 0. So let's call this maybe phi bar is the solution. Okay. So this is just a trivial mean field, and just make here the comment that, well, this in our case here, this justifies now formally that what we did before was fine. So this justifies that we early on in the diagrammatic analysis took the non-interacting ground state as a reference state around which we evolve perturbation theory. Ground state as the reference state for the diagrammatic perturbation theory. Okay, so this justifies that we earlier took the non-interacting GND ground state as a reference state for the diagrammatic perturbation. Okay, and then okay, I don't write it down, but it's or maybe I write it down. Okay, but be aware there are, for example, translational invariant problems, with inhomogeneous neutral solutions. Homogeneous. And maybe we'll have time to discuss one. Let's see. It would be like the Pyle's transition to a charge density wave solution. Okay, so be aware there are translation invariant problems with inhomogeneous mean fields, and again, the process of finding the right mean field sometimes can be a long process, like it takes a while to people figure out what is going on. So here, now it's like where we left like the pure mathematics, and now we really want to derive an effective theory. So the first thing is we have to identify the right mean field, and this is not always straightforward, because you can think of like problems in the system, and you can start with the most simple guess, but it can be that you miss some physics if you don't allow for symmetry breaking solutions. Okay, so this is often this equation can be often some source for controversial discussions. Okay, so this is like then completing the fourth step. So we identified in our case just the mean field, which is trivial, and in the last step then we should formulate an effective theory of fluctuations around this trivial mean field here, and we should at least recover like what we found from the perturbation, diagrammatic perturbation theory for the free energy if we look at the effective action. Okay, so this is like, let's make 5 minutes break and then we complete the step. Agora tem mais uma pergunta.